So something you're probably already familiar with is the idea that small particles like electrons and photons can have wavelengths. It turns out that all particles of all sizes can have wavelengths as well, and that's something that de Broglie came up with. So what did he really say? Well, he said that all matter has wave-like properties. This idea is called particle-wave duality, which is the notion that any object with mass that's moving has a wavelength. It turns out that very large objects have very small wavelengths. So it's hard to detect it. So the larger something is, the shorter the wavelength. So that corresponds to a short wavelength. If you have something that's very small, however, like a proton or electron or a photon, the wavelength is much longer. And that's why historically we typically don't have to worry about wavelengths for very large objects because they're so small. But it's important to keep in mind that anything like a baseball or even you running along a track has a wavelength. The formula used to solve for wavelength, so-called the de Broglie wavelength, is lambda is equal to h, Planck's constant, over m times v. Sometimes you'll see this equation written a little bit differently, where m and v are replaced with p, so h over p, where p stands for momentum. So what do all these variables mean? It's summarized right here. Lambda represents the wavelength of your object. Planck's constant is represented here by h. You have your mass, velocity, and your momentum, which is p. All right, so let's try to apply that equation to a problem that you might see on an exam. It says, determine the wavelength of an electron, they give us the mass, moving at 5.31 times 10 to the 6 meters per second, and then compare this wavelength to that of a baseball moving at the same speed. So let's go ahead and try that. So the first thing I would do is write the formula for the de Broglie wavelength, which is h over mv. And we're looking for wavelength, so we can plug in, right? So it's as easy as plug and chug, 6.63 times 10 to the negative 34 joules times seconds, all over the mass. Remember again that you don't have to memorize any of these constants. They're always going to be given for you. 9.11 times 10 to the negative 31 kilograms multiplied by the velocity, 5.31 times 10 to the 6th meters per second. Our units are going to cancel, and we're going to get our final units of wavelength, which is a unit of length, and units will be meters. We plug this into our calculator, and we get 1.37 times 10 to the negative 10 meters. So that would be your final answer. Sometimes they might ask you to convert to nanometers. If you wanted to, you could totally do that. If not, you can leave it in scientific notation. The second part of the question asks us to compare this to the wavelength of a baseball moving the same speed. So essentially what it's asking is, if you had a baseball moving at this velocity, would the wavelength of the baseball be larger or smaller? All right? So we said earlier that large objects, so big objects, have short wavelengths, whereas small objects have long wavelengths. So then what would the wavelength of a baseball be? Well, a baseball is bigger than an electron. Because it's bigger, it has a shorter wavelength. So we would say that the baseball would have a shorter wavelength. Why? Because it's larger. It has a bigger mass. And things with bigger masses have smaller wavelengths. Okay, so let's try a different example. So this example says, suppose that a basketball and a baseball have the same de Broglie wavelength. Are their velocities the same or different? If different, which is moving faster? And then explain. All right, so let's write our equation down. Our equation is lambda equals h over mv. What they tell us is that these two items, basketball and baseball, have the same wavelength. All right? So that means in both cases, lambda is constant. Now, what are they asking? They're asking, are the velocities going to be the same or different? Well, we know that between a basketball and a basketball is much bigger. So we know that the masses are different. Baseball is much smaller. So if the masses are different, the velocities are also going to have to be different in order for lambda to be a constant. All right? So a basketball's mass is larger, so the mass is larger for a basketball, meaning that the velocity for the basketball needs to be smaller. So we would say that velocity of the larger object, which is the basketball, is smaller. And the reason for this is in order to make the momentum constant. So we could say required to keep momentum constant. In other words, same as that of baseball. And remember again that momentum is the product of m and v. So here all they're asking for is qualitative. It's a qualitative question. You know, you're just as likely to see a question like this as you are a quantitative question that asks you to perform a calculation.